So in this case, we are going to consider a typical example that is working with the regenerative method or the Hopkinson's method, which is the Hopkinson's back-to-back test. So if you're to consider the information that we are given, it was stating the following results were recorded during a Hopkinson's back-to-back test conducted on two similar shunt wound machines. All right, so like I actually mentioned on the introduction, that we are going to apply the Hopkinson's back-to-back test on two similar shunt wound machines. One is going to be a motor and another one is going to be a generator. So just a basic view for those who missed the class. If you are given something of this nature, that is, we are going to consider the motor and also consider the generator, where the motor on its own, it has its properties. Considering the field of the motor, the resistance or the current that is going to flow in the field, the current of the armature, which is affecting the motor, the current that is the load current of the motor entering the motor, current 1 and current 2. These two are entering here. That is the sum. Considering this side of the generator, we have got the armature current of the generator, the part of the field which is affecting the field, and so on. So just the basic, we are going to relate that one as we are answering our questions. So quickly, going through the information, already you were given the information. So when you are answering these questions, I said for equal efficiencies, this is what you had when you were actually in N3, that one, you worked with it. Then for equal ion friction and windage losses, this is the one that we have additionals that we need in our N6. So to answer this question, you have your diagram. All right, I'm just going to show you the steps that you need. So this information needs to be inserted on the diagram. All right, so the diagram is just going to be similar to this one, only that you're just going to remove these ammeter, the voltmeters, and so on. So this is what you're going to have. Let us just have the diagram first before we attempt our questions, guys. All right, so we have, remember, these are two similar machines and the setup is one and the same. One is going to be having a generator and a motor. So we're gonna have a motor this side. Okay, so this is the side where we have the motor. All right, and this other side we are going to have a generator. So that is it. I'm just gonna have something that we can just use here. All right, so let us have the part of our generator. All right, so the generator, it must have its winding, the field winding here. This is the part of the field winding. The motor also must have its field winding on this other side. All right, so just a basic view, guys. This is our motor and this is our generator. So as we do understand that the generator, it supplies the current. It supplies the current, the generator. So if it supplies the current, therefore it means we are going to have the armature current from this side, from here, going up. All right, so the arrow is supposed to be going up. That is where we are going to have the armature current. This side, we are going to have the field, because we have got the field here of the generator. These two machines are similar, so they have the same resistance of the armature. All right, so as the armature current of the generator supplies, remember at this point we've got a junction. So we are going to have another current going this side, another current going this side, which is the load current. So this side, we are going to have the load current of the generator. This is the generator side. All right. On this side of the supply, we are going to have the voltage definitely here of from the supply, the current, which is from the supply, which is referred as I2, that is from the supply. Okay. So as we can see that I1 and I2, they are flowing in the same direction. So these two currents will enter at this point. Okay. Remember your Kirchhoff's laws. This current is going this side, this one is going. So both are entering here. So definitely we are going to have the sum of these two, I1 plus I2, which is the motor's current, the motor's load current. Just like the generator's load current, I1 plus I2 is the motor's load current. Okay, then it enters, as we can see from our supply. This one is now the motor's load current. It enters at this junction, here. So meaning to say another current is going to branch into the field, another one to the motor, which is the armature of the motor. So we've got the armature current of the motor. This side, we are going to have the field current of the motor. So this is just like a basic view of what you're given. All right, so understand this. Your currents, flow of currents is very, very important because it is going to help you in determining some of the information. You'll see it as we are answering our questions. So let us just quickly insert what we are given. So you're given that the supply voltage is 200. So that is the supply voltage we're already given. Here is 200 volts. We also have the current drawn from the supply, which is from supply. Remember, this is the part of our supply. So that is I2, which is 15 amps. They are working from the what? From the supply. Then the motor's armature current, 100 amps. The motors, the part of the motor here, that is where we are given the armature current of the motor. So what is the armature current of the motor? So we are given this one as 100 amps. All right, so that is 100 amps. Then also we are given the motor's field current, 3 amps. The motor's field current, all right, this is part of the motor, remember? So we have got 3 amps here. Then the generator's field current, okay, which is this one, generator's field current 2,5. Generator's field current, we are on the generator. We are given the field current, which is 2,5 amps. All right. So when you're answering, let's say you are in exam, guys, you are answering the question because they will give you these questions and it depends with the information what exactly do they want you to do on the calculations. Are you calculating for equal efficiencies or for equal ion, friction, and windage losses? For these equal ion, friction, and windage losses, you need this diagram. There's no need, you need this diagram because you have to calculate, or you need a lot of values that you have to calculate. For equal efficiencies, let's say they actually give you the information is direct. Sometimes there is no need for you to have a diagram. Unless those currents that because you're going to talk about the formulas, you see that they need the currents. You're going to need I1, you're going to need I1 and I1 plus I2. So still the diagram is needed. So this is just a simple diagram, guys. Know your diagram, okay, the flow of currents, then fill in your diagram before attempting your questions. All right, so we have the armature circuit resistance of each, because they're identical, they have the same. That's 0.05, the same armature current there of each machine that we are having. That is the generator and the motor. They have the same armature circuit resistance. So because we do not have other like components affecting the circuit, the armature circuit, we're just going to take that one as the as RA. That is the resistance of the armature circuit, yes. But we do not have any other resistance affecting that armature. So we're just going to take it to be of the armature direct as it is, which is 0.05 ohms, which is the same even on this side, 0.05 ohms. So we have that one. It's already given. Okay. If we are to move on, we can see that here, we want to fill in the currents now. So let's see which side is easier. This information, guys, I want you to be very careful here. This information is going to differ here. It is going to differ with the question, the currents that you are given. So you figure out, you are not going to expect to have a similar diagram that has got the flow of currents like this. On our diagram, let's figure out which side is it easier to work with. Is it going to be from the motor or from the generator? Or is it going to be from these currents, I1 and I2? From what we are given, we can see that from the generator, guys, it's difficult because we are only given one current, this one, IF. We do not have armature current. We do not have I1. We just have IF. So it's difficult. On the motor, we can figure out something because of our Kirchhoff's, all right? Our Kirchhoff's law, guys, the current here is flowing. It enters here. So another one branches here. Another one branches here. Remember that the current that is entering will be the sum. So this one is simply going to be the sum. Okay, let's just use this one for the ones that we are filling in. All right. So we are just going to add these two currents that are flowing away from the junction. That is 100 plus 3. So this is going to be 103 amps. Simple like that. So we are simply saying, according to our diagram, I1 plus I2 is simply the sum of IA and what? IF from your Kirchhoff's. Current that is flowing towards the junction is equal to the ones that are flowing away. So those ones that are flowing from the junction, you add them. All right. So that was going to be 103. So like I said, it depends. Sometimes they give you I2 and I1. You work from there, you add these two, they're entering here, you add them. So it depends. So we have got 100 there. All right. From here, we can find I1 because we can see that I2 is entering, all right? It's flowing towards this junction. I1 is also flowing towards this junction. So it's just like an equation, guys. Remember your mathematical skills. It's just like I1 plus this one that is also both these two, they are flowing towards. So it's I1 plus what? Plus 15, which is supposed to give us this 103. So what is I1? I1 is simply going to be 103 minus 15, which is 88. All right, so we managed to calculate this one. That is 88 amps. Okay, let's move on to another part. Since we now have this I1 and IF, we can calculate the armature current here. From the same concept, the armature current flows towards the junction. It branches another one here, another one here. So it simply tells us that the armature current from the generator is the sum of these two. It is the sum of the load current and the field current. So just going to add those 288 plus 2.5. All right. So that was going to give us 90.5 amps. So we have got this one also, 90.5 amps. Guys, if you are answering this type of a question and your diagram is like this, you are not going to have any challenges. Everything is clear when it is like this. You can answer your question. So sometimes they can even tempt you guys as you are answering questions in exam. They put this information, then they'll ask you to draw the diagram later on the last question. Whether they ask you to draw that diagram on the last question, as an individual, make sure that that diagram is there. Do not consider the question they're asking that on the last question. No. As an individual, make sure that the diagram is already there because it's going to help you. Sometimes you do not have this, you do not have these currents, and it is from another branch that you have to work from that will lead to these currents that you need on your formulas. So it is important to know your diagram. This flow of currents is all about the Kirchhoff's law. All right. So on the first part, the question was to determine or to calculate the efficiency of each machine, assuming that they have equal efficiencies. So guys, you are calculating efficiency and they are telling you that they have equal efficiencies. So what does it mean? It simply means the efficiency of the generator and that efficiency of the motor is the same. They have the same equal efficiencies. These two are equal. All right, so that is the first part that you're given. So for equal efficiencies, I mentioned that you're going to use this formula. That is the one that you had from your N3 electrotechnology. All right, we are going to work with the generator's load current, the square root of the generator's load current over the motor's load current. So that is the simple formula that you have there. Generator's load current over the motor's load current. I1 plus I2, this one is the motor's load current. Remember, I mentioned this before, I1 plus I2. This one is the motor's load current. All right, I1, this is the generator's load current, just like that. Okay, so that is what you need. So if you see, guys, from our diagram, we already have these values. So it is just a matter of substituting. That is the importance of having your diagram. I1, you already have it, the generator's load current. Remember, we calculated this, we got 88. So that was going to be 88. So we've got 88 over I1 plus I2, which is the motor's current. We calculated this one. Remember, we got 103. The motor's current, it was 103. Just like that. You multiply it to 100%, whatever that you're going to have at the end. You have what you refer to as the efficiency. For equal efficiencies, you use this formula. All right. So that was going to give you something like 92.432%. Just like that. So for equal efficiencies, guys, your formula is just direct like this. All right. So you just need your diagram. As you can see, once you have those currents, you just need to substitute, then determine your current, your efficiency. Then for equal ion, friction, and windage losses, which you can use the letter C to represent these losses. All right, so when you are given this type of a question, you're going to follow these stages. I said you have to draw the circuit diagram. You said direction. So if you check on the steps that I listed, these are the ones that you have already done here. To fill in the diagram, everything you've already filled in your diagram, like what you need. So this is your information, guys. You have filled in, then you go back to the calculations of the efficiencies. All right. For the efficiencies, guys, let me do this for the sake of time, because I listed these formulas on the introduction, and also, guys, I referred, if you still remember, there's a video that I talked about these ones so that we do not waste time. So these are the formulas that you have at the end, guys. We talked about finding efficiency on a motor. Any one of these formulas. This is a basic view that you have. So if you are to take it now to the basic view, let's use the last formula, this one, where you have already divided this and everything. So because just going to take that last formula for the motor so that we see how to apply it on our question here. All right, so that is the part B for what? For equal ion. All right, so let me just write for equal C. For equal ion, what, or you can just write in short like this, ion and F losses, like that. So this is it. They said our question under exam, they will specify for the generator or for the motor. There they said calculate the efficiency of each, meaning to say for the motor and for the what? For the generator. And we saw that from our formula. All right, so let us just consider a motor. I just want you to see the formula so that you also understand what exactly are we going to work with in our calculations, depending with the way that you understand. All right. So depending with your calculations, guys, this is what we saw here. We can have P in minus losses over this P in. We can have this one as 1 minus losses over V in. So if you are using this one for 1 minus losses over voltage times the load current, we are going to make adjustments on our formula because here we are saying this current is the load current for the motor. So according to our diagram, what is the load current for the motor? The motor's load current is I1 plus I2. So that is why you see this formula being adjusted now written as 1 minus losses like this over V, since the load current there to the motor is given as I1 plus I2. You end up having your formula like this. So I explained these formulas, guys, on the introductions. So make sure that you go through the introductions. I think it can help. You end up having a formula like this on the part of what? The P in of the motor, wherever you have the P in, this one. If you're using this, wherever you have that P in on the motor, now it is going to be V into I1 plus I2. That is what you have, guys. It's because of the diagram that you're working. Nothing has changed on the formulas. No. It is because of the diagram. The motor's current is given by this, according to our diagram. So meaning to say on the generator also, so here, guys, I'm just going to explain from those formulas. On the generator, we saw that there is a load current there. According to our diagram, what is the load current? Our load current is I1. So meaning to say, as you are working with the generator, wherever there is the load current, you're going to use what? I1, because that is the load current of the generator according to our diagram. So where this P out is being, where you're calculating the output power, voltage times the load current that you are referring is of what? Of the generator, which is I1 according to our diagram. So this one is because of the diagram that you are working with. All right. Anyways, this is it, guys. We are going to have our formulas listed later on that we are going to use in calculations. So this formula, I'm going to have it again. No problem. Do not worry. I'm going to have my formula again, but you can write it, no problem. So once you know these formulas, you saw that the losses there that we are talking about, these losses, these are the three losses. I mentioned about the three losses that you need to apply: the shunt field copper loss, the armature copper loss, and that part of the iron friction and windage losses. So those are the ones that you need, the losses. All right. So guys, these are like a follow-up steps. All right. So on this part, please just follow up here. This is how you are going to do, because you see on your formula, you need what? Losses. If you're dealing with a motor, if you're dealing with a generator, you are going to need these losses. So let's calculate our losses, all right? So let's calculate losses. So guys, you look into the formula and see, okay, this is what I'm supposed to calculate. So the first part, these two losses, we can even combine them on a table. We can just write for a motor and this side for a generator. So these two, which is the copper losses, all right? For the copper losses, guys, you can combine them, okay? I talked about this also on the introduction that you can combine the copper losses. So the first one, we have got the shunt field copper loss. So we're gonna have the shunt field copper loss. All right, so the shunt, guys, it's all about the voltage and the field current. You remember, you're talking about the shunt, the part of the shunt field. So the voltage and the field. If you are given RF, you can use RF and current, but as you can see, we do not have that one. So this is what you're going to do. On the motor, you calculate the shunt field copper loss on the motor. Okay, so our terminal voltage is there on the motor, 200. The field current of the motor is 3. Of the motor, this is your motor, guys, is 3.
So that's 200 times 3. So be careful there. 200 times 3. That's why you see some they use the letter M to is the motor. If it is the generator, they'll use the letter G for the generator, guys. That part is your own presentation. If you understand that one, you can put that. But if you understand this is the motor, so the field current that I'm using there is from what? Is from the motor. You won't even go wrong. All right. So multiplying these two, we're going to obtain 600 watts. So it is the same thing. The shunt field copper loss that we calculated, but this time we are going to calculate it under what? Under the generator using the same formula, guys. Voltage times what? The field current, but it's from the generator, meaning to say the field current is of the generator now. If you check here, we have the field current from the generator side. The field current is there. So terminal voltage times the field current of the generator. So that's 2,5. 200 times what? 200 times 2,5, just like that. So that will be 200 times 2,5. So this was going to give us 500 watts. Okay, so this is from the generator. We do the same thing for the armature copper loss. We remember these are the copper losses. So the ones that you combine are the copper losses because these ones can be calculated from formulas. Same formulas, but only different values like what you're working with. All right. So we've got the armature copper loss, like I said, armature copper loss. So for the armature copper loss, remember we are dealing with the armature. So we need the armature current and the resistance of the armature circuit. And looking into our circuit, we saw that there is nothing that is affecting that armature circuit. It's just the armature. So just take that resistance of the armature, guys, as it is. So do not worry about that. All right. So this is it, guys. But we have to consider, because they are different, for the motor, what is the armature current of the motor? So you have to take the armature current of what? The motor. All right. Looking into our diagram, so that the armature current of the motor here is what? 100. Okay. The motor armature current there is 100. And the resistance of the armature is the same for both machines, 0.05. All right. So that's 100 squared times 0.05. All right, so that was going to give us the armature copper loss of 500 watts. So this one was going to be 500 watts. You do the same thing, calculate the armature copper loss this side, but of what? The generator, meaning to say the armature current must be of the generator. From the generator side, what is the armature current? We check from the generator, armature current, we have it. That is 90,5. We calculated this. The resistance of the armature is the same. So that's 90,5 squared. That's current squared, remember? So 90,5 squared times the resistance of the armature, which is the same, 0.05. So that was going to give us to 3 decimal places, it was going to be 409,513. It was going to be 5125. So it went to 3 decimal places, guys. All right. So that's it. So we have all the copper losses for both machines, for both. Whether the question here, I want you to be careful when answering this because you might be asking the question to say, are we going to have the table? If the question was just calculate the efficiency and they specify of the motor. These losses, whether it was calculate the efficiency of each machine, whether it was calculate the efficiency of a motor, of the motor, or taking it as a motor or taking it as a generator, these losses you're going to need there for both machines. This part here is what you do. Whether the question is specifying it's a generator or a motor, you calculate these ones. Why? Because we will need these to calculate the ion friction and windage losses, those other losses, because you need the total copper losses. Okay, so I mentioned that also you are going to need what? The total copper losses. So I said, guys, for each machine, we are going to need C. All right. So there we are done. We need the third one, which is C. All right. Which are the ion, friction, and windage losses. But for each machine, it is called C over 2. All right. So you need to calculate the ion, friction, what losses, whatever that you have, but they must be divided by 2. Why are we going to divide those losses by 2? It is because they are being shared equally. They are being shared equally. And in our case, no power, no output power is going to be taken out. So the output power is equal to 0. So understanding that the output power is equal to 0. Remember, guys, when you are calculating this from the flow, from the flow of energy, you know that the input is equal to output plus what? Plus the losses. But in this case, we are saying the output is 0. So the input will be equal to what? The input will be equal to losses. So if the input is equal to losses, which losses are we talking about? The 3 losses. The 3 losses, meaning to say we are talking about the total copper losses, these ones. All right. The 3 losses will include the total copper losses. Remember, there are 2. Plus this one of the friction, ion, friction, and windage losses. Those are the ones that are now there. So we are now considering the total copper loss. Like I said, we're going to consider the total copper loss and what? Ion, friction, and windage losses. Because we do not have the output. So as we need this one, because we need it as C over 2. So we need this C first. So how can we find it? We're just going to take it to this side so that it will be what? The subject. So it's going to be input minus total copper losses. That will give us C, which is our friction, ion, and what? Windage losses. So as we can see, guys, on our formula, total copper losses is needed. So we need the total of these losses that we just calculated. So the total copper losses was gonna be what? You add everything for both machines that you're calculating here on top. These are our copper losses, remember. So you add everything. The first one, it was 600 plus this one, it was 500 plus this one, it's 500 plus this one, it's 409.513. You add all these losses together. So that was the total copper loss according to our information, combining everything. This was going to give us 2009,513 watts. So these are the total copper loss. As we can see, guys, you need them here. Yes, we can just write them here direct on the formula. It's up to you. So therefore, C, which is our ion, friction, and windage losses. So this one, remember, that is your ion. All right. Let me just do this. I and F loss in short. So this is it. So we can substitute now, guys, as we can see the input now can be calculated. We do not have this one. The input, all right, we never calculated this one. But we are just going back here to the diagram. The input there, it is not the input to the motor. It is not the input to the generator. It is the input from the supply. That is the one that you're talking about. Guys, I refer to the input of the motor on that efficiency formula. This is not on efficiency formula. This is the input of the circuit. So you take the voltage, terminal voltage, and its load current, which is I2. So that's V times I2. So we have that one. All right. So we have that one, guys. So this is what you're going to have. So simply C is going to be P in, which is V times I2 minus the total copper losses. All right. So meaning to say V times I2, guys, we saw our terminal voltage is 200 The load current on the supply is 15. So that is it. You subtract the total copper losses as you added these together. That is it. So this was going to give us something like 3,000 minus this one. It was going to give us 990.487 watts. So this is C. So this C, guys, is the total. But remember, we are considering for each now, because they are being shared equally. These losses are being shared equally. That is why even you see the way that the copper losses, we included everything. So this is the total, guys. This one is our total ion, friction, and windage losses. This is the total of it. But that's not what we want, because we need efficiency on each machine at the end, each. So that is why we have to calculate this C over 2 for each machine. It's now for each machine, because they are being shared equally. So you're going to divide whatever that you got here, you divide it by 2. That's 990.487 divide by 2. So that was going to give us 495.244 watts, like this. So this is it. So guys, I want you to be careful on this stage. You need the 3 losses on calculating of the efficiency of each machine, whether it is a motor, it is a generator. You need the 3 losses. You need these 3 losses. The shunt field copper loss. We are also going to need the armature copper loss. We are also going to need the friction and windage loss. But because they're being shared, this C of the ion friction and windage, we're just going to use it C over 2. These are the 3 losses that you needed. So you have the losses, meaning to say efficiency can be calculated. All right. So I mentioned, guys, that you see textbooks are there to bring you like formulas, which is true, which is fine. But on those formulas, also be careful, because it is an idea of someone who is just trying to bring like, I have this formula now. There's nothing like that to say I have a new formula. The formula for calculating efficiency does not change. It's the same output over input. Guys, the formula for calculating efficiency is the same. Knowing this formula, knowing that efficiency is input, this one, input minus losses over input times 100% for a motor, when working with a motor, is enough for me to calculate efficiency. This part of dividing this and that, I explained that it's not even necessary. It's not even necessary, that part. If you want to use it, because now it's like if you're even you're even checking question papers, you see they use this formula, then no, guys, this formula is enough. So if you want, you can even use that. So that is it. I just wanted you to know that is just one and the same thing. So let's calculate our efficiencies, guys. For a motor, just gonna start with a motor. So for a motor, whether you took the formula, which was, remember, output over input, and we ended up with formula like this: P in minus losses over P in like this times 100%. I'm going to use this one first and take another one also and show you that it's just one and the same. Whether you're using this one, it's one and the same, as long you understand what is here. These are the 3 losses that you calculated. What about the input? The input that now we are talking about is the input to the motor. We are dealing with the motor now. What is the input to the motor? Voltage times what? Times the load current to the motor. The one that I was explaining there on our diagram, to say the load current to the motor's load current is what? I1 plus I2. You are no longer just taking any current. There is of the motor that you are taking, I1 plus I2. All right, so I'm just going to explain this formula, then I explain the other one, guys. It's just one and the same formula. Do not worry. Let's just finish up. That's I1 plus I2. So meaning to say here, we're just gonna fill in our information. That is it. So the input voltage times the load current to the motor, the input, the voltage there, it was 200, the terminal voltage. Let's just quickly check. Yes, that's 200. And I1 plus I2 is I1 plus I2 is 103. So that's 200 times 103. All right, 200 times 103. Just like that. So this is your input, guys. So you've got your input 200 by 103 like this, minus the three losses that you calculated, but these three losses, they are on the what? On the mod. You are no longer taking all of them to say the ones even for the generator there, because there are also losses, this one that we have for the generator. No, you work with those ones for the motor. For the motor. So let us take our three losses in that case, only considering the motor. So we have got the armature, the shunt field copper loss 600. So we're just gonna combine all of them. So that's 600. Just gonna put a bracket here. We have the armature copper loss. Remember, we're on the side of the motor. Armature copper loss, it was 500 plus this one. Iron, friction, and windage losses is the same. Remember, we said for each machine. So it is used here on a motor, it is used on a generator. This one is the one that is the same. It is equally shared. So we're going to use that one as it. That is why you have to divide by 2. We calculated the total first, then we divided it by 2. So this is the one that you're going to take. 495,244, like that. So this is our C over 2 ion friction and windage losses that is for each machine. Everything over what? According to this formula, everything is over the input, this same input that you had. Remember, our input, we said, is 200 times 103. Just like that. So this is what you're going to have at the end. You can calculate your efficiency from there. Knowing your efficiency formulas, guys, it is important. So that was going to give us 92,256%. That's for a motor, when considering this as a motor. So it is up to you the way that you're going to present your formulas, guys. You have presented your formulas using the one of efficiency of a model. It's now on the formula that you are using there. You use the one that has got 1 minus the losses over the input, which is voltage times the load current. But remember, I was specifying that our load current, which is the motor's load current, is given by what? I1 plus I2. Whether you're using this formula, guys, you're going to simply have the same answers. Remember your three losses. So still you're going to have the same answer. The efficiency of the motor, you're going to insert your values 1 minus. This is a single fraction. So you add all the losses here together, all the losses that you just added there on a motor. Remember, we had 600 plus 500 plus 3, it was 4. 95,244 on the motor. Everything over voltage times what? The load current. The terminal voltage is 200. The load current I1 plus I2 from our diagram, remember, it was what? 103. Just like that. Still, you're going to have the same answer. Same percentage, 92.256%. So you've calculated the efficiency for a motor. All right, that was our first one, our first part. We move on to the second one for a generator. Remember, they said for each machine, for each. The question is asking you to calculate the efficiency for each machine. So let's move on to the generator. So on a generator, we are simply going to use the same thing, same application, but what is it that we are now applying on our formulas? Like I was mentioning that The formula was still the same, but now the load current is now referred as I1 according to the diagram that we are using. It is because of the diagram that we are using here. The part of the generator, the load current on the generator is I1. So that is it. So knowing these guys is very, very important. Your formulas for efficiency, generator and motor, know the difference, all right? So that's it. So just gonna have another one for a what? For a generator. Let us quickly have our formula. So for the generator, we saw that the formula, that will be output over output plus what? Losses times 100%. So you can even determine the output on its own, or you can just substitute output. That's voltage times current on a generator. Voltage times the load current plus the losses. The losses, these are the three losses that we calculated, all right? So this is the formula that we are simply going to use, substitute our values. That's it, we are done. That's for the generator. Voltage times load current, remember, that is on our diagram. The load current of the generator is 88. Voltage is 200. So that's 200 times 88. All right. So you're going to have 200 times 88, everything over what? So this is just a single value. The same value that we are having there, 200 times 88 plus the three losses that we are referring are on the generator. Be careful there. On for a generator, meaning to say we are going to add the same copper losses that we had, but on a generator. Remember, we're dealing with a generator also. So we're going to take this one, 500, 409. All right, so let's add our losses together. So you saw that there is a 500 watts there. There is a 409,513. All right. Third loss is that one, the C over 2, the ion and friction. Ion friction windage loss is C over 2 because it was shared equally, this one. So it is going to be used for both. You use it on a motor, you use it on a generator. All right. So this one is the same. So that is our C over 2 for the ion what. So let us take this one, substitute into our formula. We are done. So that was 495.244. All right, so with this information, efficiency was going to be calculated, guys. Make sure that you use your calculator properly. You were going to obtain the efficiency of 92.608%. This is the efficiency of the generator when considered as a generator. So they will specify in exam. They are going to specify, is it the efficiency considered as a motor? Is it the efficiency considered as a generator? They are going to specify that one. But whether they specified or they said it's just for both, like what our question was, these losses, guys, never skip any one of these. This table you calculate for both because you need, remember, we needed this to obtain the total copper loss that we need, that we use to calculate the ion friction and windage losses together. Remember, we needed this from the total copper loss where we ended up with P in minus the total copper loss. So that is why you need for both. Yes, when you are now calculating to say, now I'm calculating the efficiency of the generator. I am on the formula of efficiency now, on the formula here. The three losses that you write here are only for the generator here. Here. You are dealing with what? A generator. So list the ones of a generator. So take note about this last one. It is shared equally for both machines. It is there on the motor. It is there on the generator. So do not confuse with the last one for the ion, friction, and windage losses. So that is how questions might be given working with the regenerative method, which is our Hopkinson's back-to-back test. So we need now to work with question papers. So not to miss any of these classes, working with introductions, working with question papers. Make sure that you become part of the membership family so that all the introductions will be in your hands before your exams. So that's it, guys. Till we meet again.